Yeah, so maybe we can start the session, Carlo, if you are ready. It is okay to start?
Yes, I'm ready. So can you hear me well?
Yes, very well.
Yes.
Okay, very well. So it is a pleasure for me to chair this second session of TAUP, and I welcome everybody. So this session is on neutrinos, and we have three interesting talks of neutrinos. And I encourage people to put the questions in the chat so they can I can read them after the talks. So let me introduce the first talk by Stefano Gariazzo on sterile neutrinos. So Stefano, you can start.
Okay, thank you very much, Carlo, and thank you all the organizers to give me the opportunity to present this talk. In this talk, I will try to say as much as I can about light sterile neutrinos, and let's start from motivations from the very beginning. So why do we need a sterile neutrino and why it must be light? So we know very well that neutrino oscillations were confirmed by Super Kamiokande and the SNOW experiments. They won the Nobel Prize in 2015 for discovering that neutrino oscillate. What does that mean? Well, it means that we have two bases to describe neutrinos. One is the interaction basis. Neutrinos are defined by the flavor of the corresponding lepton. And one is the mass basis, where the neutrinos are defined by the mass and how they propagate. So neutrino experiments normally involve some source that produces neutrinos of some flavor alpha and tries to detect neutrinos with a different flavor beta after some propagation at a distant cell. And the neutrinos, which will have an energy E, will have a probability to change flavor from alpha to beta, which is proportional to this quantity. This includes the neutrino mixing matrix and an exponential that depends on the mass splittings times the distance divided by the energy. So using this formula, we can test the neutrino oscillation parameters, and this is a short summary of one of our most recent global fits by the Valencia group. We are preparing an update. You will find it in the web page soon. You see that here we have 6 parameters. The mixing matrix is described by by 3 mixing angles and 1 CP violating phase, and plus we have the 2 mass splittings. Most of these parameters are rather well known. There are few uncertainties. For example, we don't know the mass ordering, we don't know the exact value of the CP violating phase, and as you can see in this plot, we also don't know if θ23 is below or above 0.5, so the sine square of θ23. Does this paradigm explain all the experimental results? Well, the actual answer is no. We know that there are anomalies. These anomalies are known since many years. The first one was proposed by LSND in 2001. LSND observed an excess of events, of electron antineutrino events in a flux of muon antineutrinos with a significance around 4 sigma. Then in 2011, we had 2 new anomalies. One is the gallium anomaly with a significance of almost 3 sigma, and then the reactor anomaly that is also around 3 sigma. Both involve disappearance of electron neutrinos or antineutrinos. And the last anomalous results is Minibun, which is also the one that claims to have the largest anomaly, close to 5 sigma. And again, Minibun was built in order to test the LSND anomaly. So what do these anomalies have in common? The fact that they cannot be explained by 3 neutrino oscillations for different reasons. And a possible explanation would be to have an additional mass splitting, a third mass splitting, which should be around 1 electron volt squared. Of course, if we want an additional mass splitting, we want to have at least 4 neutrinos. So what happens with the fact that we know that there are 3 families of leptons? Well, that is not a problem because the lab experiments actually tested that there are 3 neutrinos that interact with the zeta boson. But in principle, there can be more than 3 neutrinos, with just the caveat that they are sterile. We call them sterile because they do not have interaction with the standard model particles. So they are basically right-handed fermions in the standard model. If we introduce new neutrinos, we have to change a little bit our description of the mixing paradigm. In that case, we will have 3 active neutrinos, those that interact with the standard model particles, plus n-3 sterile neutrinos. There will be n massive neutrinos, and the mixing matrix will be typically n times n. In the rest of the talk, I will focus on the case where we have 3 active and just 1 sterile neutrino. And we assume this model to be a perturbation of the 3 neutrinos case. So in general, we want the mixing matrix element here to be small, the orange ones and the magenta ones. This one should be close to 1, and the green one should be mostly unperturbed with respect to the 3 neutrino case. We also assume that the sterile neutrino has a mass much larger than the active neutrinos, so that it oscillates much faster, and that means that the oscillations due to the active sterile mixing are visible at short distances. We will also have new mixing angles, 3 new CP phases and new Majorana phases, but I will not talk about the CP phases. So in our scenarios, we have 3 + 1 neutrinos, and I said we have 3 mixing angles that describe active sterile mixing. We are only interested in the last column of the mixing matrix, which is the one that is described by only by the 3 new mixing angles, because we consider short baseline experiments. At short baselines, the mixing angle that correspond to the 3 active neutrinos do not affect oscillations. And we actually have 2 kinds of experiments. One is the disappearance class, where we detect how many of the initially produced neutrinos with some flavor alpha remain in the detector. We can have electron channel or muon channel, respectively, for reactor and gallium experiments, or for accelerator and atmospheric experiments. And this disappearance experiment mainly tests 1 mixing angle at a time. So this is θ14 for the case of reactor and gallium experiments, and mostly θ24 for the atmospheric and accelerator ones. The other type of experiments is appearance, when we try to detect if there are oscillations that produce some new flavor that was not present in the source. In that case, you see that the effective mixing angle has a different formula, and it's actually the product of 2 mixing matrix elements. As I said, these should be small in order to have the 3 + 1 scenario as a perturbation of the 3 active neutrino case. And therefore, this product should be quadratically suppressed. So first problem I will show you is that the minimum detector, which tests neutrinos traveling at a distance of around 500 meters and with an energy of few hundred MeV to few GeV, prefers actually maximal mixing. You see here that the best fit is at a sin square equal to 1. And of course, this is not quadratically suppressed at all. And there is also another problem with minimum, which is that you see that the excess at low energies cannot be explained even assuming maximal mixing. So one of the 4 anomalies, minimum, it seems suspicious. So we do not know what happens at low energies. We cannot have maximal mixing, otherwise we cannot satisfy the 3 + 1 requirements. We have to wait for microboon. I will not discuss more in details this because I have no time. Let's abandon for a second oscillations, and let's talk about something else. And the sterile neutrino affects not only oscillation experiments, but also other type of constraints can be derived. One of them is beta decay. So the beta decay process is a process which considers some kind of nucleons, which decays emitting 1 electron and 1 antineutrino of the electron flavor in this case. By studying the energy spectrum of the electron, we can test the mass of the neutrinos. In this case, it's the effective mass of the electron antineutrino. This is due to the fact that the presence of a neutrino mass introduces a shift in the endpoint. So this is actually an approximated formula. The true formula must take into account the presence of different mass eigenstates and different mixing with the electron flavor. So this is the full expression of the Curie function. And this is an example that I produced considering 3 neutrinos with mass of 0.5, 1, and 1.5 electron volts, and all they have the same mixing with electron flavor. So we see two different types of effect. The lightest neutrino introduces a shift in the endpoint of the energy spectrum of the electrons, but the other mass eigenstates also contribute by introducing a kink in the energy spectrum, and there is one kink in principle for each mass eigenstate. So let's consider the sterile neutrino case. This is an example considering a mixing of 1% and the mass around 1 electron volt. Okay, the kink is very hard to see from this plot, but the contribution of the sterile neutrino is here. Catherine, in principle, could detect the presence of a kink. You see this simulation by the Catherine experiment with a mass of 10 electron volts for the sterile neutrino. And of course, if Catherine can detect the presence of sterile neutrino, it can put bounds on the presence of active sterile neutrino mixing. And in particular, this is a plot which is taken by one of the most recent Catherine results. In blue, you see the constraint with the current data, and in the dotted line represents the future constraints when Catherine will have the full data set. It's interesting to compare the future constraints with the results from reactor experiments that I will mention later. We see that the Catherine is nowadays not observing any active sterile mixing, not even presence of the fourth neutrino mass eigenstate, and it's not competitive with the other type of experiments. But in the future, it can start to test the reactor constraints. In particular, this is the best fit of neutrino 4. Another class of experiments which can constrain the sterile neutrino is cosmology. And the idea is that if we introduce a new particle, it should be produced in the early universe, not through weak interactions in the case of the sterile neutrino, because it does not take part into weak interactions, but it should be produced by oscillations. The point is that if we compare the interaction strength, the interaction rate in the early universe, which is in red, with the oscillations rates in yellow for the active sterile oscillations, and in green or in blue for the standard oscillations, we have to take into account the fact that when the interactions are stronger than oscillation rates, there cannot be oscillations, because the neutrinos are always kept in the flavor basis. They cannot oscillate, they cannot change to the mass basis and therefore oscillate. So that means if the mass splitting is around 1 electron volt, that active sterile oscillations start with the temperature of the universe was around, let's say, 25 MeV. Depending on the mixing angle, this can be enough in order to bring the sterile neutrino in equilibrium with the active neutrinos. And how much the sterile neutrino contributes to the energy density of the radiation in early universe is quantified by N effective. And in particular, we call delta N effective the contribution from the additional neutrino, the sterile neutrino. We expect N effective to be delta N effective to be 0, or N effective to be close to 3 if there is no sterile neutrino, or delta N effective close to 1 and N effective close to 4 if it is fully thermalized. So there are approximations that one can consider. This is 1+1 approximation. In order to have the full picture, you have to solve numerically the equations. And we do that using Fortepiano, which is public. You can download it and compute whatever you need. Fortepiano allows to vary more than one angle at each time. And in this case, for example, I am showing the plot of how an effective varies as a function of this mixing with the electron flavor and of the mass splitting. These are the constraints which in 2019 were the 3 sigma best fit region from reactor experiments. You see that they correspond to the yellow region, which is an effective but basically close to 4. So with large mixing angle, the sterile neutrino is fully produced in the early universe. With small mixing angles, an effective is basically 3, and we have no sterile neutrino. Problem is, here we have all the mixing angles equal to 0. But if we start varying more than one mixing angle, you see that the region corresponding to an effective equal to 4 is much larger. This is because the oscillation channel work parallelly. And this also means that since the constraints from the Planck experiment tell us that an effective is basically 3, optimistically we can have a 2 sigma limit of 3.7 or something like that when considering the most optimistic constraints. A fully thermalized sterile neutrino is not allowed by cosmology, so we cannot have an effective equal to 4. So we can use the constraints on an effective in order to put bounds on the active sterile mixing angles. And this is what we did in this paper here. And you see that the constraints are almost independent on the angle. All the angles are equivalent because the cosmology cannot distinguish the flavors. There is a small difference between the electron and the other flavors, but it's not visible in this plot. It's really something small. And the CMB constraints at 2 sigma put bounds on each of the mixing matrix element to be smaller than order 10 to the minus 3. So they are quite strong constraints. Now let's come back to oscillations and let's talk about disappearance. In particular, I will start with the muon channel. So to have a full discussion of muon disappearance, we should consider several experiments. I will just present a few of them here. The first and one of the most important is MINOS and its extension MINOS Plus. These are experiments that work with 2 detectors, one at 500 meters and one at 800 kilometers, with energies of around order GeV. And MINOS Plus considers this flux of muon neutrinos, and since there are no observed anomalous events, it puts bounds on the sine square of θ24, which are basically saying that at 90%, this angle for a wide region of the parameter space is below order 10 to the minus 2. Another very important experiment is IceCube. These are the results considering the high energy events with only 1 year of data. And you see also in this case, well, the constraints in different quantity because there is a 2 here. But they are equivalent to the minus ones in this region here. IceCube also puts constraints thanks to the inner part of the detector, which is called deep core. Deep core measures neutrinos at lower energies. And in that case, we also have constraints on U mu4 and U tau4. So both the constraints are ordered 10 to the minus 2, 10 to the minus 1 in U mu4. Another very important point about IceCube is that these are the results with the high energy events from 1 year of data, but the 8-year update, which was published last year, is actually quite different. So you see that there is a preferred region, which is not so strong significance, but is still a preferred region. And it's the first time that disappearance experiment have some evidence in favor or some preference in favor of active sterile oscillations. Of course, since the significance is still very small, it's possible that the signal is just due to statistical fluctuations. We will have to wait for more data in order to understand if this preference is true or not. I will just mention that also NOVA started to put constraints on active sterile mixing. This is not a short baseline, but rather a long baseline experiment. And it's not yet competitive with the atmospheric experiments, but still it's a confirmation, and with more data they can provide probably more precise results. One of the last parts of this talk is about the electron disappearance channel. And in particular, here we have 2 anomalies, as I mentioned before. One is the reactor anomaly. The reactor anomaly appeared when the groups of Patrick Huber and the group by Müller et al. Computed the new reactor antineutrino fluxes in 2011. Using the new fluxes, there was a deficit in the observed events with respect to the prediction by compiling a number of previous experiments. And the deficit was around 3 sigma originally. And the interesting point is that the deficit could be explained by active sterile oscillations. Problem is this result relies on the absolute flux from reactors. And since 2014, we know that probably we cannot trust that much the absolute flux because several different experiments observed distortions. In particular, the distortion is between 4 and 6 MeV, and it's called the 5 MeV bump or shoulder. This distortion cannot be explained by oscillations between active and sterile neutrinos because it happens at very large distances where the oscillations are averaged out. And since we have no idea what generates the distortion, it's best to consider experiments we can measure the reactor antineutrino spectra at different distances. In such a way, we can take the ratio and do not rely on the absolute neutrino flux. And now in the next few slides, I will argue that the reactor anomaly, which was introduced by the Huber and Müller calculations, is actually disappearing. One of the reasons is that several different groups evaluated again the antineutrino flux from reactors. And there are two methods to do that. One is to convert the very old measurements of the electron energy spectrum from reactors at the IL reactors in the 80s. Another one is to compute the spectrum, basically rely on nuclear databases. And this is what the Estienne and Fallot group did in 2019. They proposed a new calculation using the nuclear databases, the updated ones. And you see that the anomaly is reduced to 1.2 sigma, so it's basically not significant anymore. Even more interesting, I think that there is this new measurement of the electron energy spectrum which updates the very old IL determinations by the Kurchatov Institute. And applying the same method that Patrick Huber applied on the IL data, they find that the new spectrum is basically compatible with the observations. So there is, if this calculation is correct, there is no anomaly at all, because the observation is perfectly in agreement with the calculation. Concerning active sterile neutrino oscillations, there are several experiments which measure the active sterile oscillation patterns using the distant dependence method. So, for example, NEOS, DANCE, Prospect, Stereo, they were all taking data since like 2-3 years. And basically all of them are now excluding the best fit, which is the original best fit of the reactor anomaly, which is this one. So the reactor anomaly as was proposed in 2011 is basically gone. A few years ago, some of these experiments were also claiming some significant observation of active sterile oscillations. Well, I don't have time to discuss this point, but it's just to say that we have to take into account the true chi-square distribution in order to compute the bounds. And with the true chi-square distribution, the bounds are normally much less significant than with the Wilks theorem. So, for example, this is a best fit of reactor experiments. You see that the best fit mixing angle is again at the level of 10 to the minus 2, but the significance is 1.8. So we cannot claim that there are sterile neutrinos from reactor experiments anymore. So I think I'm a little bit late, so I will skip the discussion about the gallium anomaly, and let's go to the last section of my talk, which is fit, or mainly global fits. So I presented until now several different experiments or constraints. Now we have to combine them all together. And the first thing we do is combine, for example, the appearance experiments all together. And we see that here in red we have Minibun, in blue we have LSND, and two vertical bands here represent the constraints by Icarus and Opera, which you see that they cut most of the 2 sigma region by Minibun. So we are left with this rather small region of parameter space here with the mixing angle between 10 to the minus 3 and 10 to the minus 2. Remember, this was the quadratically suppressed one. From the new mu disappearance, we have again a combination with constraints, basically the mixing angle to be smaller than 10 to the minus 2. This does not include the ice cube 8-year results, because I think that they are not published in a way that can be used to reproduce the results. And the problem comes when we try to combine the disappearance results. So this is the muon disappearance projected into this plane. In violet, we have the electron disappearance projected again into this plane. The disappearance probes together are represented by the red region. The red regions exclude everything on their right. So all this part of the parameter space is excluded by disappearance, but you see that this part is the one that is allowed by appearance, and there is no overlap of the 3 sigma regions. So this is called the appearance disappearance tension, and it has a p-value now that is order 10 to the minus 9. And of course, this means that the two classes of experiments are not compatible. This is also one of the reasons for which you didn't see any article about global fits of active sterile neutrino oscillations in the last 2 or 3 years, because we don't know how to do with what to do with this data. Since they are not compatible, they cannot be combined together. The only way to make them compatible is to consider a subset of the data. But for example, you need to exclude completely LSND and minibun in order to have a p-value which is compatible, p-value of 1, so perfect compatibility. And there is, of course, no reason to exclude any of these experiments unless they are probed to measure something which is not active sterile oscillations. And we have to basically wait for the next generation experiments in order to understand if that happens or not. There is another problem which I already more or less discussed earlier. So the problem is the fact that these were the reactor best fit regions like 1 year ago, more or less. And you see that the cosmological bounds exclude the reactor region. They are incompatible. So we have no quantification of this tension, but it's by eye, it's a rather strong tension. And so again, if the reactor experiments are correct and cosmology is correct, we need some new type of physics in order to solve the tension. We cannot explain all the experiments with just one sterile neutrino. And so this brings to the conclusions, which unfortunately are not very optimistic for the sterile neutrino case, because we have non-oscillation probes. All the probes observe nothing more than 3 neutrinos and put strong constraints. The oscillations probes are varied. There are several different probes that can have a significance around 3, 4, 5 sigma, but they are not compatible with one another. There are tension between the disappearance and the appearance experiments. There are tensions between the reactor experiments and cosmology, and there may be tension between reactor experiments and beta decay constraints in the future. So whatever we are observing, it's probably not a sterile neutrino, and we have to understand which kind of new physics is that. And good luck. I hope we will solve the problem soon. Thank you very much.
Oh, thank you, Stefano. Very nice talk and very clear. So I have one comment, and I think the other is a question that just appeared. So I just first will read the comment by Antonio Palazzo. He thanks for the nice review and just commented that long baseline experiments and atmospheric neutrino oscillations can be sensitive to the extra CP phases induced by sterile states, even if the oscillation induced by the new splittings are averaged out. Maybe you want to comment something about that?
Yes, so the focus of this talk was just short baseline experiments. And as I report here, the short baseline formulas do not include the delta CP phases, which normally are associated to 2 of these 3 mixing angles. So yes, that's true. With the long baseline experiments, we would be able to study also the CP violation between active and sterile neutrinos, but I just did not have time to discuss this.
Okay, yes, so we have also comment by Jose Crespo Anadon about in slide 7 you wrote about the fact that there was no money to make a near detector. I think that you referred to Minibuna on that, but
yes,
you notice
yes.
that now they have the money now, and they are constructing the detector in the new experiment SBN. Yes,
yeah. Yes, indeed. This was referred to Minibun, which is just one single detector, but the new Fermilab program, which will include the Microbun, Icarus, and the other short baseline detector, will have, of course, several detectors on the same beam line. That will be perfect in order to study active sterile oscillations, because they will have the comparison between 3 different distances.
Okay, there is also a question by Mariano Chavez. Does the new reactor fluxes calculation reduce the tension in the global analysis?
I don't think so, because so the point is that when we compute the constraints, for example, if we consider this new reactor flux calculation, there will be no short baseline anomaly from reactors from the rates, but we do not only use the rates, because all these experiments use the information from the shape of the spectrum. So I think that in that case, we probably have just to exclude the data from the reactor experiments rate measurement and to consider the shape measurement, which is actually what was done by Carlo in this paper. These are all shape experiments which are independent on the absolute flux, so that would not affect this result.
Yes, I agree with that. So the bound on UE4 will be stronger even, and so the tension will increase somehow.
Yes.
Yes. And there is a final question by Subabati. Any comment on the neutrino 4 result?
Yeah, well, I didn't mention that because I didn't really have time. There are, I think, two problems with the neutrino 4. One is that the mixing angle is rather large, so I'm not sure it can be called a small perturbation of the three-neutrino mixing paradigm. And the other thing is that the best fit of neutrino 4, which is at an angle of around 0.3 sine square of T2 θ14 equal to 0.3 and a mixing mass splitting of 7, is more or less excluded by the constraint by prospect. It should be here. So the 2 sigma exclusion by prospect excludes the best fit of neutrino 4. And so I don't know. Well, it's a little bit controversial. I'm not sure I have a backup slide on that, but Carlo, with other collaborators, also studied. Yes, I have this. The significance of the neutrino 4 results, which is shown in this paper. So I didn't have time to mention, but the problem is that we cannot consider the Wilks theorem in order to constrain the active sterile mixing parameter, because when the mixing angle is small, there can be fluctuations of the background which are better fitted by oscillations than by a straight line. So this means that for small mixing angles, even if there are no oscillations, you can have a best fit, which should indicate with the small significance that there are oscillations. If one considers the true distribution of the chi-square by doing Monte Carlo simulations, the significance of the best fit decreases a lot. And so, for example, you see here that the Wilks theorem constraints are in dashed lines, but the Monte Carlo constraints are those in solid lines. So the significance of neutrino 4, which is claimed to be more than 3 sigma by considering the Wilks theorem, is actually less than 3 sigma when one considers the true distribution of the chi-square.
Okay, Stefano, thank you. I'm sorry I have to stop this interesting discussion, and I remind everybody that is interested that the discussion can be continued in the forum that you can access through the virtual page or your personal virtual page of TAUP. So, Stefano, thank you for the nice review, and please stop sharing, and I invite the next speaker, that is Patricia Vahle, which she will speak about the long baseline neutrino oscillation review, including the future. So Patricia, please share the, okay, the slides, we can see them, and you can start when you want.
Okay, and can you hear me?
Yes, yes.
Great. So I'm very happy to be here today to tell you about long baseline neutrino oscillation experiments. So for the past 20 years or so, we've known that neutrinos have mass. So that means in addition to our familiar electron neutrino, muon neutrino, tau neutrino, the eigenstates of the weak interaction, we also have 3 mass states, nu1, nu2, nu3. And these are the eigenstates that are important when neutrinos propagate. Now, if these two sets of states are not aligned with one another, that means that we could have a non-zero probability that a neutrino created as one flavor can later be detected as another flavor. And this oscillation probability depends on the distance the neutrinos travel, the energy of the neutrinos, the differences in the squared masses of the neutrinos, and on these mixing amplitudes. Now, these mixing amplitudes are the elements of a 3x3 unitary matrix called the PMNS mixing matrix. And that matrix can be written in terms of 3 mixing angles and a possibly CP violating phase delta. Now, at this point, we've measured all of these angles. We know that θ23, the angle that's important in mixing in the atmospheric sector, is large. It's possibly maximal at 45 degrees. The angle associated with solar mixing, θ12, is also large, 34 degrees. And in fact, even the smallest of the angles, θ14, comes in at about 9 degrees. We've also measured the mass splittings. We know that there's one relatively large mass splitting that's associated with the atmospheric sector, and that mass splitting is around 2 × 10⁻³ eV squared. And then there's a smaller splitting associated with the solar sector, and that comes in at around 8 × 10⁻⁵ eV squared. Now, we've measured all of these parameters fairly well. There we go. The mixing angles, or the sine squareds of the mixing angles, we know to about the 3 or 4% level. And we've measured the big mass splitting to about the 1% level, and the smaller mass splitting we know at about 3%. But even with these relatively good measurements, there's still plenty of questions that we want to answer about neutrinos. So long baseline experiments can help us answer all the questions here that are shown in blue. And the previous talk did a very nice job explaining how long baseline experiments are involved in telling us whether they're sterile neutrinos or more than 3 neutrinos. And so I'm going to concentrate on the other 3 questions on this slide today. So the first of these questions, the first of these questions regards the θ23 value. We want to know whether that angle is really 45 degrees. Do we have maximal mixing in this sector, or is θ23 just a little bit above 45 degrees in the upper octant, or is it just a little bit below 45 degrees in the lower octant? We also want to know the value of this phase delta. If this phase is not 0 or not pi, then that means there's CP violation in the neutrino sector. And the final question we would like to answer using long baseline experiments is the mass hierarchy, or the mass ordering. What order are the neutrino masses arranged in? Do we have 2 light neutrinos and 1 heavy neutrino? Do we have a normal mass ordering? Or are we in the inverted mass ordering, where we have 1 light neutrino and 2 heavy neutrinos? Now, the answers to these questions have profound impacts on our understanding of the universe. Very specifically, if we can find CP violation in the neutrino sector, that may help us understand the matter-antimatter asymmetry of the universe. But more broadly, 20 years on, we're still exploring how massive neutrinos fit into the standard model. And discrimination among different alternatives hinges on precision measurements of all these parameters and the answers to the questions on the previous slide. So now let me introduce you to the experiments. There are 2 currently running long baseline experiments. On the left here in the United States, we have the NOVA experiment, which measures a beam of neutrinos produced at Fermilab just outside of Chicago and sends them 810 kilometers up to northern Minnesota, where we measure them in a FAR detector. In Japan, there's the Tdk experiment. Tdk takes its neutrinos from the J-Park facility. They travel all the way across the width of Japan, 295 kilometers, where they're detected in the Super Kamiokande detector. Now, in both of these experiments, we study multiple oscillation modes, so nu-mu, disappearance, and nu-e, electron-neutrino appearance, and we compare the oscillation probabilities that we measure with neutrinos and separately with antineutrinos to extract all the oscillation parameters. Now, having these 2 different experiments at different baselines and different energies really complements one another. And ultimately, having these 2 experiments may help us to resolve remaining degeneracies in the oscillation parameters if the two experiments or either experiment can't resolve them individually. So both of these experiments use high power but conventional neutrino beams. So that means we take high energy protons and then bombard a target with those protons. And in those collisions, we make hadrons, mostly pions and kaons. We focus those hadrons into a collimated beam using focusing elements or focusing horns. And we also use those focusing devices to sign select the beam so that we can make either a neutrino beam or an anti-neutrino beam. Once those hadrons are collimated into a nice beam, they enter a decay volume where they're allowed to decay, mostly into muons and muon-type neutrinos. Tdk uses 30 JeV protons as its original source, and it achieved a power of 515 kilowatts back in 2020. NOVA uses a higher energy proton beam, 120 JeV protons, and we recently achieved a power of 843 kilowatts. Both of the experiments are off-axis experiments. And what I mean by that is that the detectors are not located along the central axis of the beam. They're actually placed off-axis of the beam. And this is useful because of this equation in the center here. So the neutrino energy depends on the original energy of the parent that produced that neutrino, but it also depends on the decay angle. And you can see that illustrated down here. So this plot shows the neutrino energy as a function of pion energy in this case. And if you're on the axis of the beam, you get this black line. The neutrino energy is completely linearly dependent on the pion energy. However, when you go off the central axis, you can see that this dependence is sort of washed out and you lose the dependence of the neutrino energy on the original parent energy. And you can end up with more neutrinos at a particular energy where you want them and fewer neutrinos at different energies. So specifically, NOVA is at 14 milliradians off axis. And that means we see a narrow band beam that's peaked at 2 GeV. This energy is well matched to where we expect the energy we expect the oscillation maximum to be at. So it means we have lots of neutrinos at that oscillation peak, but we have few high energy neutrinos that can interact via the neutral current interaction and look like a low energy electron neutrino interaction. Tdk is similarly off axis, it's further off axis, it's at 43 milliradians off axis, and they use a beam peak around 600 MeV, which is again well matched to the expected position of the oscillation maximum at their baseline. So both experiments, NOVA and Tdk, use a two detector technique. That means they both have near detectors to measure the beams up close before any oscillations have occurred, and they use that as the control for the experiment. So data recorded in the near detector is directly used to predict or constrain what should be seen in the far detector. And it is also used to understand and mitigate many of the effects of systematic uncertainties in the experiments. So to the left on this slide, you can see the NOVA near detector. We say that the NOVA near detector is functionally identical to our far detector. And by that, we mean that it uses the same technology for neutrino detection. We built it out of the same materials. It's just a smaller size version of the detector. In Tdk, they have a suite of near detectors. They have the INGRID detector on axis, and this is used largely for beam monitoring. And then at the same off-axis angle as Super Kamiokande, they have the ND280 detector. And this is a fine-grained detector that they use to measure neutrino interactions that informs their prediction of the far detector spectrum. Recently, Tdk also added a new detector. This detector is at a different off-axis angle at 1.5 degrees off-axis. And while this detector is up and running and taking measurements, it's not yet used to constrain their oscillation measurements. The way that the two experiments use their near detectors differs somewhat between the two detectors. In Tdk, they take 18 different samples measured in the ND280 that are separated out by muon charge and multiplicity, and they fit these samples with a parameterized version of their flux and cross-section models. And so to the right, you can see an example of just one of these 18 different samples. This is a nu-mu charge current sample with no pions. The top, you're seeing the muon momentum distribution of that muon, and the top is before their fit, and then after is below is after they adjust their model to better match all of those data samples. In NOVA, we adjust our flex and cross-section models guided largely by external data. We then further adjust our simulation to account for poorly simulated multinucleon processes. And then we extrapolate any remaining discrepancies between our data and Monte Carlo that we see in the near detector in bins of both energy resolution and now transverse momentum using a far over near ratio that we take from the simulation. And so the left two plots show you near detector nu-mu charge current data reconstructed energy spectra. The top plot is what we see in neutrino mode, and then the bottom plot is what we see in anti-neutrino mode. And of course, both experiments use far detectors that you can see in the background here. Tdk uses the Super Kamiokande detector, which is a 50 kiloton water Cherenkov detector. You can see the photomultiplier tubes of that detector in the background here. And then in NOVA, our far detector is a 14 kiloton detector made out of PVC filled with liquid scintillator. And to the right here, you can see the PVC cells of the detector that are then filled with the active liquid scintillator elements. All right, so now that I've told you about the experiments, let me switch gears and tell you how we do the analyses. So in 0th order, what we want to do is compare electron-neutrino appearance probability measured in neutrinos to the same quantity measured using antineutrinos. And so to the left here, you can see an illustration of this. This shows you the probability of electron antineutrino appearance in a muon neutrino beam, muon antineutrino beam, versus the probability of electron neutrino appearance. And this is for the NOVA experiment with our 810 kilometer baseline. So let me explain this plot a little bit. So first of all, in vacuum, if you had no CP violation, you would expect the same oscillation probability between neutrinos and antineutrinos. So if you went away and measured these quantities, your answer would lie on the diagonal of this plot. However, if there is CP violation, that is going to enhance your neutrino oscillation probability while suppressing the antineutrino oscillation probability, or vice versa. And so different values of delta CP will give you different values on this plot. And if you go around in delta, you trace out an ellipse in the biprobability plot. Our neutrinos are traveling through matter. So matter effects will also introduce differences between neutrinos and antineutrinos. And these differences depend on the mass ordering or the mass hierarchy. So you can get, again, an enhancement of neutrinos with a suppression of antineutrino probability, or vice versa. And so your ellipses split into two different ellipses, one for the normal ordering here in blue, and then one for the inverted ordering shown in red. There's a final complicating factor, and that's of the octant of the value of theta 2,3. The upper octant will enhance the oscillation probability for both neutrinos and antineutrinos at the same time, while values in the lower octant will suppress them both. And so now we have three sets of ellipses here for three different values of sine squared theta 2,3, 0.04, 0.5, 0.5, and 0.6. Here's the same plot now for Tdk, and you can see that the ellipses move somewhat. First of all, Tdk's shorter baseline means that there's a smaller difference due to the mass ordering, so the two ellipses overlap one another more. And if you look at the extremes, you can get a plus or minus 10% effect from the mass ordering in Tdk, whereas it's a plus or minus 20% effect in NOVA. Tdk also has an L over E to really optimize the CP violation measurement. So to optimize the differences that you would get for different values of the CP phase delta. NOVA actually runs a little bit above the oscillation maximum so that we can optimize our hierarchy determination, whereas Tdk runs right on that oscillation maximum. So if you look around the ellipses are a little bit wider, and so CP violation or CP effects give you a plus or minus 30% effect in Tdk compared to about a 20% effect in nova. Now, these biprobability plots and ellipses are useful for understanding how the different oscillation parameters come into play in the measurements. However, to get the full sensitivity of the experiments, both experiments fit both disappearance energy spectra and the appearance data to extract the oscillation parameters. So in all the results you're going to see, it's more than just event counts that go into it. It's full fits to both disappearance, appearance, and the full energy spectrum in both neutrinos and antineutrinos. So here is that data. This is Tdk far detector data. And so I won't belabor the details here. Instead, I'll direct you to the discussion panel sessions for any questions you might have on the details of what gets fit. But I will show you some results. So this first set of plots shows you fit results from Tdk. On the left-hand side, you're seeing values of delta Cp on the vertical axis versus values of sine squared theta 1, 3. So Tdk does two different types of fit. First, they fit leaving all the parameters float, letting all the parameters float. And then they also constrain the value of theta 1, 3 to the reactor experiment results. And so blue is where they let everything float, and then red is if they constrain to the reactor. They find that their fit to theta 1, 3 is completely consistent with the reactor experiments to better than 1 sigma. So for the rest of the results they show, they apply that reactor constraint so they can extract the most sensitivity to their other oscillation parameters. So the best fit from Tdk is in the normal ordering scenario and also in the upper octant of theta 2, 3. And they find that their data prefer maximal CP violation. Their best fit value of delta M squared is about 2.49 times 10 to the minus 3 EV squared, and sine squared theta 2, 3 is 0.546. Their data have a weak preference for the normal ordering and also a weak preference for the upper octant on the order of one-ish sigma. They do, however, have evidence for CP. They do exclude CP conservation at 90%. And you can see that in the plot below. This shows delta chi squared as a function of delta CP. Blue is for the normal ordering. Orange is for the inverted ordering. Their best fit is over here near maximal CP violation, negative pi over 2. And then the shaded regions show you the values that are allowed at different confidence levels. So these diagonal lines here show you the region allowed at 90%. And you can see that both pi and 0 are excluded at 90%. Minus pi is allowed at the 2 sigma level, where 0 is excluded at the 2 sigma level. So now here is NOVA far detector data. Again, I'll leave the details to the parallel sessions, but I will show you some results from NOVA. Here on the left, you're seeing allowed regions of sine squared theta 2, 3 versus delta CP. And we show you for the normal hierarchy in the inverted hierarchy, and the different shaded colors show you the different significances, what regions that are allowed at the different significances. Over here, you can see a similar plot that you saw for Tdk. This is the significance with which we disfavor a particular scenario as a function of delta CP. This is for 4 combinations of the hierarchy or the ordering and the octant combination. So NOVA, our best fit is also in the normal ordering case and in the upper octant. We find a delta M squared 3.2 a little bit smaller, 2.41 times 10 to the minus 3 EV squared. Sine squared theta 2, 3 just a little bit bigger than Tdk, 0.57. And our value of delta CP comes out at about 0.82 times pi. Do notice that we use a different delta convention than Tdk. We let delta run from 0 to 2 pi instead of minus pi to pi. In NOVA, we also have weak preferences for the normal hierarchy, the upper octant, and non-maximal mixing. So these are all about 1 sigma level significance. But we do exclude combinations of parameters at high significance. So we exclude the inverted hierarchy or inverted ordering case at delta CP of pi over 2 at greater than 3 sigma. And in the normal hierarchy, we exclude delta at 3 pi over 2 at about the more than the 2 sigma level. So here are some plots that show comparisons. The first thing is over here to the right. This shows you delta m squared 3,2 as a function of sine squared theta 2,3. So these are the atmospheric mixing parameters. And you can see that the world's measurement of these atmospheric mass splitting and mixing angle do show good agreement. So black here is nova, red is Tdk, and then the other ones here is green, the Minos plus long baseline experiment. And then you can also see Super Kamiokande and then Ice Cube here, and all agree relatively well. This is at the 90% confidence level. If you look at the results now in terms of sine squared theta 2,3 and delta CP, you can see a little bit of tension between the nova and the Tdk results. So here in blue shaded regions are the nova results again. This is now the 68% confidence level region and the 90. And then you can compare it to the Tdk contours, 68 and 90%. And this is just for the normal hierarchy here. You can see the Tdk best fit value is in a region that nova does not prefer at the 90% confidence level, though there is overlap between the two allowed regions. So this difference in the best fit values is largely because nova does not see a strong neutrino-antineutrino asymmetry when we look at electron-neutrino appearance, whereas Tdk does observe more electron-neutrino appearance than electron-antineutrino appearance. And that's illustrated down in these plots at the bottom. So now instead of probability, this is showing you antineutrino mode, number of electron-like candidates. And then on the horizontal axis, this is for neutrino mode. And here's where the Tdk data lie. And then here you can compare two ellipses for different values of sine squared theta 2,3. And with the data being out here, it really does prefer these lobes of the ellipses where you have maximal CP violation and you are in the normal hierarchy. You can compare that to what nova sees, again, antineutrino events versus neutrino events. And the nova data are kind of nestled here in the middle amongst all of these ellipses. So this explains why we don't have a strong preference for a single hierarchy or a single octant, but it shows that we don't see strong asymmetries between our neutrino and our antineutrino data. So you can look at that in one other way as a function of energy by computing the appearance probability. And so these are plots from nova showing oscillation probability for electron neutrino appearance. And on the right is electron antineutrino appearance. The black points are the nova measurement. And then the curves compare to different oscillation predictions for different oscillation parameters. So in particular, you can compare the black data to the gray curve here, which is generated using the Tdk best fit values. So this is for neutrinos, and then again for antineutrinos, here's the nova data, and then here's the prediction using Tdk best fit parameters. We can look at this one more way. We can take the difference of these two oscillation probabilities, divide by the sum, and we can look at the asymmetry in the oscillation probability between neutrinos and antineutrinos. And again, here are the black points for the nova measurement as a function of reconstructed energy. So nova data is consistent with no asymmetry between neutrinos and antineutrinos, and that's within 20 to 25%. The error bars here are 20 and 25% on the asymmetry. This error is mostly statistical, and so it will come down as we collect more data. So just a little bit on the outlook. Nova projects 60 to 70 times 10 to the 20 protons on target through 2026. With this exposure, we should be able to achieve a 3 sigma resolution of the mass hierarchy for large regions of delta CP range. And we should have a 2 sigma determination of CP violation in favorable cases. Tdk is also taking more data. They project 3 sigma median sensitivity to CP violation, and they can achieve that with 20 times 10 to the 21 POT, protons on target. In addition to collecting more data individually, we are also working together on a joint analysis, combining our data to see if we can understand some of these tensions and perhaps better resolve the oscillation parameters and the degeneracies amongst those oscillation parameters. There are a number of future projects in the works, long baseline experiments in the works. Again, here in the United States, we have the DUNE project being built. DUNE is another long baseline experiment based at Fermilab that will send a 1.2 megawatt neutrino beam to be constructed down to a detector, new detector that's being built in South Dakota. DUNE expects to easily achieve a mass ordering resolution, so they should achieve 5 sigma mass ordering resolution after 2 years running with their nominal detector design and beam configuration. And then over here, you can see the sensitivities to CP violation for 2 different run lengths, a 7-year run length and a 10-year run length. And so DUNE should be able to achieve CP violation for 50% of the delta values with a 10-year run at the 5 sigma level. And DUNE is expected to start late this decade, late in the 2020s. The other expected long baseline experiment to come online is the Hyper-K experiment. Hyper-K is a gigantic neutrino detector. It's 10 times the size of Super K. And they'll also utilize a megawatt beam from the upgraded J-Park facility. And Hyper-K is expected to start running in 2027. Over here, you can see the sensitivity of Hyper-K to CP violation as a function of delta CP. Sorry. The different curves here show different systematic assumptions. But the idea here is in a 10-year run, Hyper-K should be able to achieve 5 sigma sensitivity over a very wide range of delta CP values. So in summary, 23 years on from the discovery of neutrino mass and oscillations, we still have many exciting discoveries in neutrino physics to make. Both NOVA and Tdk have rich data sets, and we're continuing to collect more data. And DUNE and Hyper-K are doing active research and development and construction, and they both expect to come online later this decade. Thank you.
Thank you, Patricia, for the very nice talk. I don't see any question, so I invite people to make some question. I can ask you, so you say that the NOVA and T2K collaboration, they are trying to make a combined analysis, so just to understand what is the difference or the result, what is the time scale when we expect to have this analysis?
So we are aiming for next year to have at least an initial result. We are currently meeting every few months together to discuss how to put these results together. We're at the stage where we're actually doing technical work. We're sharing likelihood surfaces and trying to understand how they can come together and how we best account for systematic uncertainties and how we can run the fits and get the results out. So we're making good progress, but we're still probably maybe a year away.
Okay. And there is no other pertinent question. And so let me also ask about the future. So you mentioned DUNE and Hyper-K, but as far as I remember, there are also some other long baseline, at least proposal, not approved projects. So is there something else besides the DUNE and Hyper-K?
Yeah, so I am not aware of anything that is as concrete as DUNE and Hyper-K. These are certainly the 2 big ones that lots of money is being invested in to make them successful. And there's real equipment on the ground being assembled for these two experiments.
Okay, thank you. So there is a question by Ushak Rahman. Do you expect the tension between nova and T2K to be a result of the systematic uncertainty?
Yeah, I don't think we know at this point. I would be hesitant to attribute it to anything in particular. I did highlight one talk that will address it at this conference. There are physics reasons why there might be some tension between Tdk nova, in particular non-standard interactions in the matter. Since we have different baselines, you might expect different effects between the two experiments. But I will direct people to the talk in the parallel session for more details on that.
Okay, thank you, Patricia. So I think we must move to the next talk. So please stop sharing your slides, and I invite Carla Bonifazi to share the slides. So she will talk about the sevens, namely coherent elastic neutrino-nucleus scattering.
Yes, hello. Did you see my slide, right?
We can see your screen. I think now we can see your slide. Yes, good. So okay. You can start.
Okay, thank you. So thanks. First of all, I would like to thanks for the invitation to participate of this conference and the opportunity to talk about this coherent elastic neutrino nucleus scattering effort that we are doing. So in the talk, I will give a little general overview on what is going on this subject. Mainly, this overview is going to be from the experimental point of view, and I also will focus on the latest results that we have for the experiments and some future perspectives. So just to be sure that everybody is in the same page, we will define the sevens, that is the acronym we use for coherent elastic neutrino nucleus scattering, as the interaction where the neutrino is scattered to the nucleus as a whole by exchanging the boson. What we will see is the recoil of the nucleus. So this interaction was predicted a long time ago. It was predicted by Friedman in the 1974. In the paper, he said that this interaction will be very difficult to observe, and he was right, because it took more than 40 years to be able to measure the coherent neutrino-nucleus scattering, and this was done in 2017 by the Coherent collaboration. So this is the first measure of the interaction, and here in the plot we can see the rate when there's no neutrino beam compared with the rate measure with when we have the beam on, and it's very clear that they saw the sevens. So focusing a bit on the energy scale that we are talking about when we talk about sevens. Here you can see all the different interactions of the neutrino. The kind of interaction will depend on the energy range. So in the highest energy, we can see the deep inelastic scattering. That is a process where the nucleus is completely destroyed. And for the case of the sevens, we are talking about the opposite regimen, in which the interaction is fully elastic. The nucleus rests as it is. So the interaction we will see, as I already say, as a recoil of the nucleus, and this recoil is going to be a teeny bit. Sevens then is a process that is very dominant at very low energy. We will see that this energy threshold is about 50 MeV for a mild mass nucleus. So the cross sections, because this interaction is coherent, have an enhancement due to the fact that the 3-moment transfer times the nucleus radius is much less than 1. So we can think that all the waveforms are in phase of the nucleons. And here we can see how the cross section looks like, and this cross section will depend on the atomic number of the nucleon and also of the neutron number of the nucleus. And since the protons are multiplied by the contribution by the weak mixing angle, and this weak mixing angle is near to a quarter. So the contribution of the proton is very much suppressed, and we will observe the contribution of the neutron. So that's why the cross sections goes as a square of the number of neutrons. So also the cross section will depend on the form factor. For this low energy, the form factor is very close to 1, but we will have in large masses target, we will have a dependence on this form factor, and this will allow us to access to nuclear physics too. So here we can see how these cross sections enhance compared to the well-known other interactions. Here for comparison, we have the inverse beta decay. So this will allow us to do some more compact experiments than the huge ones that we are very common in neutrinos. So there's a price that we have to pay for this enhancement on the cross section, and the price is related to the recoil energy that, as I already say, is very low and is in the range of the few less than few tenths of kilo electron volts. Because of that, is very difficult to measure, and we need a very low threshold detector for that. And this is one of the reasons that we have to wait more than 40 years to get the first measure. But thanks to all the efforts coming from the dark matter community for the dark matter detection, so now we have very low background and threshold detectors. The same detectors that are being used for those searches on the dark matter can be used to measure the coherent scattered neutrino-nucleus. So thanks to that, now we can access to this interaction. One of the reasons to study the sevens is, of course, that since our dark matter detector can see sevens, it's very important to characterize, because 7 is going to be the floor of those experiments. So the experiments are getting more and more sensitive. So then we are going to detect in our dark matter experiment some neutrinos coming from natural sources like solar neutrinos or supernova neutrinos or the atmospheric neutrinos. So because of that, it's very important to characterize as much as we can this interaction. But of course, this is not the only reason we want to study 7. So in fact, there are many other reasons. With 7, we can use to study fundamental neutrinos. By doing that, we can, for example, have very precise cross-section measurements, and also we can do some precise determination of the Weinberg angle. This is possible because the weak charge depends on the Weinberg number, so we can access to that too. Then, of course, also we can explore for new physics beyond the standard model. So there are so many things that we can list here. So I put some of them, and there's a lot of reference, so a lot of possibility to check or to confirm with the experiment. So For example, we can look for non-standard neutrino interactions, and also to study some properties of the electromagnetic properties of the neutrinos. And in this conference, we will have some contribution about that in the parallel. So everything is going to be in the neutrino 6, that is going to be September 1st. So if you are interested in that, you can join the discussion. So many experiments already were proving and trying to put some constraints on the light mediators, interactions. Also with the 7th, you can study some action light particle production by the gamma ray flux on the reactors, and detect this in the low threshold detectors that we install close by. And also it's possible to study sterile neutrinos and some dark matter detection related. So as you can see, there's a lot of room for trying to understand not only the standard model, but also for looking new physics. So then also by studying the 7th, we can explore the nuclear physics. I already say something, going through the form factor. So we know that for large mass materials, the 3 momentum transfer will be larger, and then we will have a suppression of the cross section. This can be observed. We are very sensitive to that, 5% uncertainty on the event rate. So there's something that we can access. And also, since the Z boson coupled mostly with the neutrons, it's possible to access to the neutron form factor by studying the radius of the neutron. And this is something that is very difficult to measure, and by using 7s, we can also have more inside information for that. There's this nice paper about that, and also I want to say that having the distribution of the radius is also important for not only for nuclear physics but also for the astrophysical sector, because this is correlated with the state equation for example, in neutron stars and so on. So it's really study 7 will give us an access to determination of the neutron radius. Continuing in astrophysical, we can also say that the 7th is very important for the supernova neutrino, since all the energy is released in those neutrinos, and the energy of those neutrinos is tens of MeV. So the interaction is going to be by 7s mainly. So by studying that, we can get much better models for the supernova neutrino, and also we can use these very massive detectors that we have for dark matter also to detect neutrino from supernova. And just to finish on this list, we can mention the reactor physics. So by studying the 7th, we can use this detection as a tool for monitoring the nuclear reactors and study in detail the process of the fission process at the different moment of the reactor. We know that the fuel component change with the age they are inside the reactor, sorry. So this is very important to have a much precise models on that, and also this opens the possibility to have very compact detector for 7 that can be used also for those detection for non-proliferation purpose. So this is a long list. Of course, for detecting this 7th process, we need neutrino sources, and the requirement of these neutrino sources are the requirement that any source of particles we would like to have. This is a high flux of particles produced, that this flux can be very well understood and modeled. The detector should be in a very low background area or shield to reach this low rate in order to be more possible the detection. And also to have different flavors of these neutrinos in order to explore different properties. So basically we have two kinds of sources. One is the beams, neutrinos coming from beams, from stopped pion beams. So when the pion decays at the rest, the neutrino is produced, we produce a prompt of mu neutrinos, and then from the decays of the muons, we have the neutrino of the electron and the antineutrino of the muon. So the energy for those production is a middle energy at 30, more or less, the prompt is at 30 MeV. With that, we can access to the lower part of the seventh regime. So the other possibility is to go to the nuclear reactors. So nuclear reactors produce a lot of neutrinos, a very high flux, roughly 10 to the 20 neutrinos per second for a gigawatt power reactor. The energies are much lower than the neutrinos from the pion beams, mostly between 1 or 2 MeV. So we can access to a very coherent regime with not a dependence or almost no dependence on the form factor. And we can achieve a very clean background by using passive and active shielding. So if we see the map around the world of all the efforts that are going on or coming soon concerning this, we can see that the area is very busy. Here I split in 3 categories. So we have the stopped pion beams, then we have the nuclear reactor, and some future unplanned propositions that are going on. So starting with Coherent, that is the main experiment happening at the stopped pion beams. They have several, as you can see here, they have several detectors in the spallation neutron source of 1 GeV proton beam. So here we can see the energy produced by the prompt that is in red, that is the mu nu. And then with some delay, we will have the contribution of the other 2 neutrino flavors. So Coherence, as I already said, was the first experiment to detect the 7. This was in 2017. For that, they did the detection with a cesium iodide scintillation crystal of 15 kilograms. It was placed at 20 meters of the source, and they observed 134 events, while they were expecting from the standard model 173. The significance of this detection was almost 7 sigma, so it was huge significance. And here we can see the sensitivity of the experiment. This detection was confirmed in the second analysis with twice the statistics. This was done last year. There's a clear no rejection of the 7s. Now the significance is almost 12 sigma. And because of that, thanks to that, they could see the cross section, and the value that they got is compatible with the standard model prediction within 1 sigma. So also we can see in comparison between the result of 2019 and 2020 that they improve a lot of the uncertainties. The dominant uncertainty for the moment, systematic uncertainty, is the knowledge of the flux, but on the rest they really improve. The systematic global uncertainty is 13%, sorry. And also they detect coherence 7s with the argon detector, that is 24 kilogram massive detector placed at roughly 30 meters of the source. This is only one phase detector. It has a threshold of 20 kiloelectron volt in nuclear recoil. And they perform two different analyses, blind analysis, in order to be robust on the data analysis, and the significance of detection is a little higher than 3 sigma. So this can be seen here, the energy of the detection, the cross-section function of the energy. And this is together with the other measurement of the cesium ionide detector, shows for the first time the dependence of the cross-section with the square of the number of the neutrons predicted by the standard model. So this very near result. The collaboration is taking data, and they will continue with this also argon detector. So new results will come soon. Then there's other experimental effort going on the spallation source. Here we have the construction of the European spallation source that we will finish in 2023. And also there's a contribution of a gas detector that could be installed in this European spallation source. And this also will be discussed in the Neutrino 6 parallel session. And then in Los Alamos, the Lujan Center, the LANCE, also hosts the Coherent Capital Mills that is taking data. Also, some group of the European community have some paper with some proposition of use some of the techniques that are being used around the world, just for install new experiment in the ESS. Okay, so now we can move a little to the nuclear reactor. For that, I will start with the CONUS experiment. That is an experiment placed at 17 meters of a nuclear of the 4 gigawatt thermal reactor. This is in Germany. They have a flux, high flux of neutrino, to the 10 to the 13 neutrinos per centimeter square per second. So this is huge. The reactors is working continuously and stop 1 month for maintenance. And this month is the moment to monitor and to determine the background. So they installed 4 detectors, as we can see in the picture, with 1 kilo high pure German detectors. These are crystals with very low background. They are using a passive and an active shield, and it's amazing how they can suppress the background in a 10 to the 4-fold suppression. So it's really incredible. It's very, very good. So with this detector, also have a low threshold of 30 eV with efficiency close to 100%. So they have some runs of reactor on and reactor off, and they perform the analysis, and they were able to put some limits as a function on the events expected from the measures that they did, and these limits depends on the value of the K parameter, that is one parameter in the model of the quenching factor they are using. The quenching factor, I did not talk about that yet, but the quenching factor is the efficiency from the ionization energy that you have when you have the recoil nucleus, and this is some challenging issue on this seventh detection, because we don't have measure of quenching factor for all the materials that we are using at so much low energy. So there's a effort of the community to have those measures, and we are improving on that. And with this detection also, they were able to put a limit on this Linhart model, on the K value of the Linhart model. And also here for a value of K equal to 0.18, we can see the flux of the reactor on and off, and the difference that they have that is compatible with no observation for the moment. The other experiment that is located in Brazil, in Angra 2, is the same model of the nuclear power reactor than the one that is being used in CONUS, but the detector is outside the dome, is at 30 meters of the core. The flux is 1 order of magnitude less than that. This reactor have 1 month off each 14 months of working, of having the reactor on. The CONI collaboration installed 14 CCDs of each gram each CCD. They have a passive lead, passive shield that is mainly lead and polyethylene, and the energy threshold is very, very low, 50 eV. They are running for several years. So one of the analyses that they did by comparing the fluxes on the reactor on and the reactor off shows that a limit that with a 95% confidence level that shows that this limit is on the lower energy beam is 4 times the standard model. With this value, they were able to put some constraints on the non-standard interaction, in particular on the like vector and like scalar mediator. These limits are very competitive, and this shows the power that the low threshold detector has on the 7th detection is very promising. So the collaboration will report the news also in the neutrino 6 parallel sessions. They have another run with a binning on the detector of 5 times 1. The main goal of this binning is just to increase the signal noise ratio, and the results that they have are compatible with the previous analysis, and the limits decrease to 30 times the standard model prediction. Recently, we installed some new detectors that are named the Skipper CCD. That is a new technology on a Skipper. It's very promising technology because they will allow to decrease the threshold to 15 eV or even less. Basically, this detector have the main point is that this detector have sub-electron readout noise, and this makes a very sensitive detector at the lowest recoil energy. So this is something very, very important. Remember that at very low, the lower the energy, the increase of the number of events that we can have, and also we can access to other channels for new physics. So then in this conference also we will learn a little more about the news of NewGen detector. That is another experiment that uses high purity germanium technology. Is 1.5 kilograms. Is placed at a distance of about 10 meters of the the reactor, and we can see that the challenge, what is nice, that they can move the distance, a little the distance to the core, and by doing this, we will see that it's possible just to study some systematics. They have a passive and active shield, and the signal that they record that not shows any excess. Also, there's a new contribution of a paper that just came out from P-type point contact germanium detectors placed in the Dresden 2 reactor, and with this detector, they were able to have the first measurements with this detector, but for the moment they have a very high background due to the epithermal neutrons, so better shield and try to get a better threshold detection is needed. Also, the NEON collaboration will report his news at the conference, where they will show that they just installed the detector, that is a sodium iodide detector near the reactor in Korea. So this is very exciting because they will have a very low background, so some results we are expecting. And then we have the nucleus collaboration that has another approach of detectors, where they use calcium tungsten oxide, aluminum oxide crystals. With that, they are able also to get a 20 eV threshold. That this is very promising, and they claim that the target background will be 100 events per kilogram per day per kilo electron voltage. So this is very nice, and the experiment will place Zoom in shoes in France. They have a multi-layer passive and extremely active betas in order to reduce as much this background. So if you want to know more, go to the parallel session. Just to finish this, I want to point out this new effort that is the Violeta collaboration that aims to install the skipper CCDs, also the same technology that CONICET experiment is starting to use in Tucha-2, that is a reactor nuclear plant of 2 gigawatts, 2 gigawatts in Argentina. This effort is very promising. It's a much higher size detector in the scale of few kilograms. We can see that with this experiment, they will have much constraints on the light vector mediator, for example, and others constrained to new physics, and also they will be able to do some kind of precise measure of the mixing angle. Some preliminary measures done at Fermilab were shown in the EXES workshop, that is a workshop that aims to put all the community efforts all together and to understand where we are in terms of the quality of the detector. And we can see that the rate is very flat in all the energy range, what is something really, really good. So just to finish, let me summarize. 7 is a very active field. We are in a very exciting moment because there's a lot of experimental efforts and experiments that will have a nice result soon. So we are waiting for that. And also the community is already putting a lot of effort for new facilities and new generation experiment that will allow us to use all what we learn and do much better. And there's a huge synergy between the experiments and the theory, what is very, very good. And just to finish, this is the plot that summarizes the knowledge on the cross-section that we have for the moment. So this is just the beginning. So please don't forget to go to the session where more details about all these efforts will be discussed. And thank you very much.
Okay, thank you, Carla, for the nice talk. So we have some questions. There is one question by Arif Akundov. Have you taken into account the radiative corrections to the coherent elastic scattering, which are very important for the analysis of the experimental data?
Radiative correction?
Yes, radiative corrections.
Well, in the interaction, what you have is the recoil of the nucleus. Then this will depend how this recoil will measure in your detector. So when you do that, what you need to take into account is the efficiency of the ionization of your detector, or how this energy will go to another way to observe, like a thermal deposition or something like that. So I don't know exactly what.
So maybe
if I'm answering the question.
Yes, I can say something about that. So in the phenomenological analysis, we take into account the standard model radiative corrections, which determine the coupling to the proton and neutrons. But these corrections are very small. So in practice, they are irrelevant in comparison with the present uncertainties, which are rather large. But in the future, of course, one will need to take into account radiative corrections. There is another question by Carla Cattadori about what is the physics goal in the planning project at the European spallation source?
Well, I'm not too aware of what they are doing, but we will have this spallation source, so experiment with the technology that we are using for reactors and also in the coherent collaboration can be put there, and this source will have a high flux of neutrinos. So there are some efforts on that, and we will listen about this gallium detector. I don't know this experiment, so I think that this can be much better answered in the parallel session.
Okay, yes, there was another question by Carla about the goals and challenges of forthcoming seventh projects, but this is a very wide topic, so I think it can be discussed in the forum or in the panel session. And just a quick question, when will you get a result with skipper CCD at reactor? This is by an unknown person.
Skipper CCDs, well, now we have two detectors in the CONICET experiment. The same experimental setup that was built just to understand the low energy background at Fermila is moved to Argentina and is going to be installed in the Ciencias very soon, in the next months, I would say. So with that, we will have the first measure of these skipper CCDs at two different distance to the reactor core in parallel, one in Atucha at 8 meters, and the other one in CONI at 30 meters of the reactor core. And this is going to be a very nice thing, because we know that from other experiments that when we are inside the dome of the reactor, we would be able to see some background and neutrons coming from the reactor itself. So understanding the systematics between the two experiments is going to be very, very challenging for the better shield design for be able to work properly much near to the core inside the nuclear reactor.
Okay, thank you very well. The question was by Joan Estrada, who sent another mail with his name. So I think we are well over time, and we can close this very interesting session. TAUP will resume tomorrow. Maybe, I don't know if the organizers want to say something. If not, I think that we can close the session and see you all tomorrow. Bye-bye.
Bye. See you tomorrow.